Okay, okay, we will get started. So we'll cover the week 12 today. So is it audible? I think my YouTube videos are not audible that well. But yeah, can you hear it in the um, live sessions? Okay. But the YouTube one, the volume is really low. Do you have any suggestion how to improve it? Should I get another mic? Okay, so we'll get started. Okay, we'll get started. And I'm trying to join from here. Okay, I've joined from here, and now let's get started. So this is the last class. So how was the experience? The course is not easy, I understand. It's a really challenging course, uh, but still, I hope you learned something. Are there any sample papers? Yeah, I asked them, the NPTL people. They did not share any actually, so I cannot share back as well. Let me just check if I've got something. They haven't sent me anything, so sample papers I don't know, maybe are not in policy. Course went well and interesting. Are there theoretical questions? There mostly will be theoretical questions. Yes. Well, thanks IR for the fine review. Some critical review would be welcome as well. Okay, so that it is possible to improve. I mean, my friends who see the YouTube videos, they say the videos are not of such good quality actually. But students say they are okay. Okay. So wish you the best of luck for the exams. Okay, so this is the last part, contrastive learning and self-supervised learning that we have here. We will do that. Come on. Then we get to the questions after this. Uh, Where is it gone? uh, Week 12, page 1. Week, I'm getting it somehow. Yeah. Okay. So, okay, in assignment, out of two option, one was correct, but they gave my whole answer wrong. Okay, so which question is it? Which question, if you can point? Assignment 12. Acha, it's already done. So let's go to assignment 12 then. And out of two option, assignment 12. Which question out of in assignment 12? Okay. Or maybe we should get the first lecture done, then I can look at it out. Okay, that's a good idea. So so this is face recognition, a very simple problem. Okay, and so the history, face recognition, a typical face detection, face alignment, face matching. Those are the things involved here. Uh, so here. So here, as you can see, face recognition system, there are key components. First, face processing. So there is one to many augmentation. So you compare one to many and the many to one normalization. D, feature extraction. Feature extraction is the what neural networks. Okay, not visible. So okay. Okay, so what I was going to do, here I was. Okay, so the deep feature extraction is what any neural network does. Okay, and should be visible now. Hmm. So face matching by deep features. So there are different types of face matching ways to do it. Okay, and so face pre-processing. So this is a pre-processing step. What they do, one to many augmentation, generating many patches or images or pose variation from a single image. That is what they're doing here. So many patches or images of different phase variation, as you can see, rotation and different things they have done. Many to one normalization attempt to recover canonical view of face images from one or many images of a non-frontal view. So what they do is like you are given different poses of images, but you have to extract one image that is called the canonical image, which preserves most of the information. Okay, so something like that, only one image. Okay. So despite variation, pose, lighting, expression, background, you preserve one image. Okay. Network architecture for face recognition. So there are a lot of architectures. As you can see, we have read these things as well. So not very surprising here. Verification, identification, detection, and alignment. Okay. So detection and alignment, just take the face one, face here, and then deep CNN feature extraction, and then this is verification system, identification system, whatever you have here. Okay. So face identification. So there are classes. Which person is it? Okay. Okay. So something like that. Softmax plus cross entropy. Consider large last linear layer. The subject maps to a. So we so the last linear layer has the weight W, and beta is the bias term. Okay. So we write it usually like this. Okay. So this gives the output. So you take output of the last layer, that is what they mean, and you put it into softmax function. So what you get, softmax scores or logits. Okay. uh, okay. So you put the logits into the cross entropy loss, then you get the feature embeddings. Okay. So in the feature space, the images look like this. Okay. So these are quite well separated overall, and there is not much overlap. The loss enforces good classification, nice boundaries between classes, small inter-class variance, but it does not enforce small intra-class variance. Okay. So what they say is that uh, that there is small inter-class variance. So these classes are well separated. That is what what it means. But the points inside the class are not well segregated. Okay. So that is what it means. And okay. Let me switch off the fan. Switch on the fan. Okay. So face verification, whether it is the same face, the model has detected a face. Okay. It is person this. Okay. But whether it is correct or not, so to check that. Okay. So test image, we pass it through this, and then there is some fully connected layer as well. Not able to write. There is fully connected layer here. Okay. So it produces a output. Okay. And that uh, output you compare with what you get from the model. Okay. um, so compare that to understand, so binary decision whether it is the correct face or not. Identification via verification. Lot of things here. So another important concept that we come to here is the Siamese network. Okay. So in Siamese network, as you see, there are two networks, deep CNN of certain architecture. Okay. Some number of layers of CNN, and those things can be transformers as well, vision transformers. Okay. And so the main thing in Siamese network is that the architecture of no, architecture has to be same. That's correct. But even the weights have to be same. Okay. That is called the uh, Siamese network. Okay. So put the input there, whatever your task is. Okay. So you get the feature here, then pass it through fully connected network here, and then some distance measure, some classifier is there. Okay. It's a binary decision whether they're same or not. Okay. Those type of things. So distance measure, what distance measure can be, it is So what happens is that usually while training the model, you don't use the classifier. So this is a self-supervised training, and the distance measure is what it means is we are doing a contrastive loss. Okay, we are training with a contrastive method. What does contrastive method means? So we put the embeddings of similar images closer, of different images farther away. Okay, in the latent space. So that is called the contrastive method. The distance measure means contrastive method. We are learning how to project the data into a lower dimensional space in which the similar objects, similar data samples has to be clustered together, while the different ones should be clustered away. You understand? So that is called the contrastive way of self-supervised learning. So what is self-supervised learning if you have to get to that? So self-supervised learning, there are, so while we were training, so first classifier was not used. Okay, so we were training with no labels. Okay, and so but still the model learned some structure in the data, and and so that is called self-supervised learning. Okay, so there are here we call it like pseudo labels. Okay, so when you're clustering in the lower dimensional space, what you have is, suppose you have three labels already at different places. Okay, now the fourth one has to come. Okay, so these three are like targets. Okay, these three are like the pseudo labels. So the fourth one you keep close to this or close to this or close to that. So there you have three targets or three labels here. That is why it is self-supervised. It is not unsupervised. Okay, so there is some feeling of or some sort of label still there. Okay, so something like that. So it is very simple, similar to clustering. Okay, so I I hope you have got something. It wasn't very well structured delivery of knowledge. Okay, so we are identifying which face. Okay, so face localization. First we have to do that. Frontal crop pass for identification to deep CNN. For then we pass to deep CNN model with KOA softmax multi-class classification. So from the softmax you get which class has the highest probability of occurring. Okay, so that class is the probably our answer. Okay, so using Siamese network, again the same things, verification whether they are same. So this person, first of all the label is known. Okay, whether the network is also predicting the same thing or not. Okay, so this is unknown and this is known. You compare both and you get the answer. Okay, if it tells that both have to be on the similar, uh, both have to be close, then so that is fed into the binary decision as well. Okay, so use a cross entropy loss here. So if they are close, the cross entropy, so the answer will be 1. If they are not close, the answer will be 0. Okay, so verification, that is. Okay, simple enough. And the same thing actually. So in contrastive learning, or so it is also called deep metric learning. So what we are learning is the distance metric here. So that is what they pointed out here. So we have finally got to contrastive laws. So metric learning paradigm. So we're learning the distance metric here. Okay. So when you're putting the similar embedding closer, but different embeddings, different images farther away. So what you're learning is a sense of distance. Okay. So that is called the distance metric. Okay. So that is the important thing. So contrastive loss, there are different types of contrastive loss. Pairwise contrastive loss, in which you're taking and two samples. Okay, one positive and one negative, and then you are the loss is there. Okay, so triplet loss, there are two positive and one negative. Okay, so the positive have to be kept closer, and the negative one has to be farther away. Okay, So these are the type of loss. The most popular loss is called the info NC loss. Okay, I don't know if there is it in it is in the lecture. Okay, but uh, we can okay, these losses are there. Okay, no problem. Okay, so two network can be Siamese network and then push pull. uh, I think you already know. So lower dimensional manifold we are doing it. Okay, so okay, why we are doing it lower dimensional, so that we have a compact model. Okay, compact representation which can be easily accessed, because images are high dimensional, they are not easy to process all the time. Okay, so you learn in a lower dimensional manifold. Okay, so that is what is represented as the pairwise contrastive loss. So let's see that repeat until convergence. So there are two images xi and xj in the training set. If they are different, okay, so that is 1 0. uh, oh, yj equals to no, 0 means same. Okay, so then so to decrease, so we decrease the distance. Okay, so that is what I've explained. If they are same, they have to put closer. Okay, so they have to put closer. If y equals to, so if this is 1, then they have to be moved made farther away. Okay, so that is the structure we have here. So as you can see, y equals to 0 if these are similar, y equals to 1 otherwise. Okay. And next what we have here, train a deep CNN to jointly perform identification and verification. So this is the, so let's see that. Okay, so here the identification task is that so in identification task what you're doing is that the same people, if no, identification task you're comparing prospective different people. Okay, so their features have to be made apart. Okay, but if say they are of the same person, then they have to be made closer. Okay, so what happens, so identification what you do, suppose my this is my image. Okay, and this is someone other's image, has lot of hair. Okay, now identification what it means is that whether whether this is Anirban. Okay, so you can say, you are separating these two. Okay, if this is Anirban, this is someone else. Okay, let's say Iyer, then both are different, both have to be differentiated. Okay, so that is what identification does. Verification is, suppose there are two images of me, and you have to ascertain whether they are of the same person. Okay, so they have to be made closer, right? So then only the model will conclude that they are of the same person. Okay, so that is what they have seen. So increase the interpersonal variance and reduces the intrapersonal variance. So they are made closer if they're same. If they are, if they are different, they're made far apart. Okay, so that's it. So cross entropy loss for training. Okay, so here what we are doing, we are using cross entropy loss, and cross entropy loss separates well. Okay, so and pairwise for verification, pairwise contrastive loss. So the things are there. FaceNet. So FaceNet does a triplet loss here. So in triplet loss, what you see is there is an anchor. Okay, so your anchor means like base representation. So there is negative sample. So what it means that it is of the different person, image of the different person, and of the same person. So that okay. So these have to be made closer. Okay, and these have to be farther away. Okay, so it is more sample efficient. Learning is quicker. Okay, and robust as well. Okay, so that is why triplet loss is better than taking two at a time. Okay, so that is there, but it is still there are better options still. Okay, so as you can see in a hypersphere, what you're locating the final embedding. Okay, that is there. How to choose triplets? So there is hard negative mining. So what it happens is that suppose we specifically take the negative sample in such a way. So these are the two positive one, but the negative sample is very hard to classify. Okay, so we know that it is negative one. So model learns harder. Okay, to understand these two are different, and they have to is put apart, even though it is a very hard task. Okay, so we take triplets which are actually harder to learn. Okay, if it is very easy for the model to classify, it is already farther away, then we don't take it. So that is called hard negative mining. Okay, so you only take the hard samples, only the hard negative samples that are hard to classify. Okay, so negative sample is okay. Positive sample. Acha. So positive sample. Okay, yeah. So positive sample is like two images of me. Suppose from the front one and another from the side. Okay. So that will be the same positive sample. Okay, of the same person, right? In face recognition, it is like that. In some other task, it can be something else. Okay. Okay. And now hard triplet mining. So what we see that if the very hard samples are taken early on, then what happens that the local minima is bad, and the model collapses. Okay, so it is very hard for the model to learn. Okay, so it is gradually made hard. Okay, so semi hard negatives that we call, and improving over triplet loss, angular softmax loss. So this is another. I think this is the what you call influency loss. So let's understand this well. This is maybe the most important thing. So comparison among softmax, modified softmax logs and A softmax logs. In this toy experiment, we consider CNN to learn 2D features on the subset of the Cassia face dataset. In specific, we set the output dimension of fully connected network as 2. Okay, so there are 2. Visualize the learned features. Yellow dots represents the first class phase features, while the purple dots represent the second class phase features. One can see the feature learned by the original softmax logs cannot be classified simply via angles, while the modified softmax logs can. So original softmax logs. So we are actually trying to classify on an angle. So we are looking on. So this is the classifier, right? But it is having some tough time. So mixing is there. But modified softmax logs, you can see from this angle it is better. A softmax log, so it has, so it doesn't have to be spread out. The main problem with this one is very spread out. Okay, so here you can see it is not spread out. It is, there is also no intermixing here. A softmax loss, so that is a better one, right? Uh, so this is a softmax loss. Okay, and so these are the modification. Okay, some substitution, some things are there. Okay, that helps. So there is cross entropy plus CL loss. Okay. So the centroid means the similar samples have to be close together. That is what it is imposing here. Okay. So with this, as you can see, this is the centroid here. So the samples have to be close to the centroid. So there is a ring loss there. But we have still not gone to the well into the details of info and C loss, which is okay. Okay. So info and C is like very similar to softmax only, but the interpretation, the derivation is quite different. Okay. So Ahana has had doubt, right? Ahana, your doubt is in question number assignment 12. You can take it up now.
4 and 5.
5. Okay. So which of the following are false for self-supervised learning? Okay. So this one is correct. Bootstrap your latent does not depend on negative sampling. Okay. Moco maintains the dictionary as a stack of data samples. Cha. Keys from the immediately process. As a stack of data samples. So in Moco, so it does maintain a just remember it fully. If I find the paper here, Moco. So, so what they do here is that so the so the mini batches are small, okay, but they maintain. So what happens in contrastive learning? You need to have a large batch size, okay. So some, but many times, okay, what you've written 2 and 4 are correct. I have given 2 and 3. Question number 4. Actually, question number 4. But if you got to this, okay, let's see that. Okay. So in contrastive learning, the main problem is that so the popular loss method is the influency loss. So in which one you have one positive sample and the rest are negative samples. Okay. So for better learning, there has to be a lot of negative samples, which leads to a very large batch size, usually 2048. Usually that is the taken. Okay. Now, so they have this Moco paper has a workaround. Okay, so how you may not maintain a large batch size but a small mini batch. Okay, but you can still uh, learn good representation. So what they do is there is momentum encoder here. Okay, so here what they do is, so this is a loss, the influency loss or softmax loss. This called, so this is influency loss, as you can see. And so dictionary as a queue. So the main problem was it was a stack. They've written a stack. Okay, stack and queue have different way of functioning. Okay, stack, the first that goes in comes first. Or am I correct? Yeah. And in queue, the first comes, so what happens in queue, cannot write. Okay, so in stack, what you have, this goes in, then this goes in, then this goes in, then this goes in. When you have to come out, the last one goes first out. Okay, and in case of queue, what happens, this goes in, if this one is goes one first, then second, then third, then fourth. Okay, something like that. So the first one that goes out is this. Okay, so the first that had gotten in goes out first as well. Okay, so that is queue. Okay, so the how that was wrong is we are maintaining a queue, not a stack. Okay, so the first thing is that, so we are maintaining a dictionary which is much larger size than the mini batch. Okay, so if you can maintain a small mini batch, then our GPU memory has may not have to be large. Okay, you can maintain a small mini batch, but the dictionary is huge. Okay, so what they do a momentum update. Okay, so theta k here is uh, I think so. Let's see. Momentum contrast trains a visual representation encoder matching encoded query Q to a dictionary of encoded keys using contrastive laws. The dictionary keys are identified on the fly by a set of data samples. The dictionary is built as a queue with the current mini batch enqueued and the oldest mini batch dequeued, decoupling it from the mini batch size. The keys are encoded by slow progressing encoder driven by a momentum update with the query encoder. Acha. So this momentum encoder is updated using a slow moving average here, as you can see this one. Okay, so theta q is the query one. Okay, so and this is the key one. So key parameters, the parameters of the key momentum encoder is updated like this way using the parameters of the query. Okay, and so here you can see uh, okay, and and so the main thing is that, so when in contrastive learning here, what we are doing, you are taking negative samples from the whole dictionary, but the the many batch that we maintain are quite small. So that is why it is a very memory efficient way of doing contrastive learning. Okay, so main importance is that here, um, but the question was not that, right? Question number 4, as you said. Okay. Classifier free guidance is a technique used in diffusion model to improve sample quality without the explicit use of a classifier. This technique involves modifying the sample process based on control parameter. If the control parameter denoted as gamma is set to 0, what does this affect on the generation process? So it removes all the guidance. Okay, so what you got here is that 2 and 3, so they get 2 and 4. Okay, and it maximizes influence of the classifier leading to highly detailed so I think that is the correct one. Yeah, why option 4? Yeah, so the thing is that, so uh, so what happens, so when you are, cannot write here, fourth is the correct one, third is not correct. Okay, so what happens when you are conditioning? Okay, so and suppose the class is that you have to generate all images of dogs. All the images will be here dogs. Okay, how many images are there? Let's say how many there are, 4 5. So the 25 images are there. So these are all the images. Okay, 25 total images, all will be of dogs. Okay, but if you don't condition, what will happen, they can be of different classes, as was in the training data. Suppose there are 100 classes, so any 25 of the 100 classes might be here. Okay, so that's what they explain here, that it can lead to more diverse samples compared to higher value of gamma. So when you're not conditioning, so it can lead to very diverse. So in 25 there can be 25 different types of animals. Okay, as the generation process is less constrained by the conditional information. The generation process is not conditioned by the class. Okay, so that is the point here. I hope it is understood now. Third is correct because it writes that it maximizes the influence of the classifier. It does not maximize, it minimizes. Okay. Okay. Let's move on. Uh, let's see here now. What more do we have here? We get started here. So unsupervised learning. So there are different types of unsupervised learning. Clustering, dimension reduction, data generation, representation learning. So these are all type of unsupervised learning. So in representation learning, the and the subclass is self-supervised learning. That is what we're going to focus in. So there has to be a pretext task, which is a false task. Okay, so that the model learns to generate good representation. Okay, but not a real task. Okay, that is what not we are going to do. Not classification, not segmentation. Some type of false task, pseudo task. Okay, to so that the model just able to learn representation for further classification or uh, regression or whatever you need to do. Okay. Uh, there are different types of self-supervised learning. Treat any part of the from any other part. Okay, so these are there. What is self-supervised learning? Deep self-supervised learning and computer vision. So we're doing image in painting. Okay, so what will be the this gap? Okay, so okay, so that is another type of self-supervised learning. There are no labels here. Okay, so the model learns to predict the gap by itself. Okay, so solving jigsaws. Okay, how means it makes the model understand the spatial orientations of the patches in an image, so that it is able to solve the jigsaw. So predicting rotations. Okay, so these are the pretext tasks. Okay, representation learning and predicting rotations. Okay, these are also there. Image colorization. Okay, so black and white, or you have to fill color into it. Okay, so first what we do, you take the colored image is there, make it black and white. Okay, and then tell that the color is this. Okay, so then that way it is able to fill the colors. Okay. uh, okay, contrastive learning based SSL. So there are different four types of SSL, self supervised learning. So contrastive learning is one of them. Okay, so we have learned a lot of contrastive learning already. uh, so this is what is called the influency loss. Okay, um, this is momentum encoder we've seen already. Okay, dictionary structured as a large FICO queue of encoded representation. First in, first out. Okay, so that is the structure of a queue. Unsupervised learning visual representation as dynamic dictionary lookup. Dictionary structured given a query X Q, query representation obtained by, so this is the representation Q from this encoder we get, and I may not be able to write here. Uh, there's key samples as well, okay. So the positive key is using a copy of the XQ with different augmentation, okay. So what it happens is that, so you have one image, okay, you make two copy with the augmentation, so they're the same image, some augmentation suppose rotated, okay, and one goes into the query, another goes into the key, okay, in every batch, if every mini batch, okay. So that is what they do, and then you apply the contrastive loss, okay. Repeatedly you do on every mini batch, but the momentum, the queue is huge, okay. So you do it every time okay, on that, and this is a memory efficient way of doing it, okay. So why not just copy it, so it does not lead to a stable learning process for the model. So better to use a slow moving exponential moving average, okay. So this was the first paper actually, so this should have been before this, okay. So in simclr you you just maintain a large batch, okay. There is no dictionary or something like that. so so simclr so the memory problem is there, okay. The number of negative samples is limited by the batch size, okay, or you have to maintain large batch size. Then bootstrap your own latent is there, okay. So here what you do, you have one image, okay. So you make, give two transformation, two views are created, then you do and then compare, okay. So this is a joint embedding architecture they use, okay. And here you don't have need to have a large batch size or a lot of negative samples, because you're comparing the two views of the same image every single iteration, okay. So as you can see, the representations come from this model, then the projection is done again, and the predictions are compared here, okay. So they use squared error loss for representation learning here, okay. And so that is how it is done now. Any doubt? Okay, you have already done this question, so we can take up this as well. Let's see some of the questions here. Feedback form. What is the effect of increasing the guidance scale in classifier free guidance? So it becomes less diverse. So this one is easy. These questions we have done already. Uh, 4 and 5 we have seen the false. Why Moko? This one is false. So this rotation, the task involves generating the correct image for the given rotated input image. We've not seen it correctly, no? In detail. Let's see. Rotation based. So what we're doing is that different rotations, different convolutions, the same convolution model. Objective maximize. Oh, so it predicts different orientation actually, not the 0 1. Okay, so process in DDPMs to remove noise? What is the forward process to add noise? What is the diffusion process in a diffusion model? Okay. Primary goal of clip. Okay, so these are all done already. Answers are already there. Okay. Now we have moved into the multimodal category, which is the vision language model. So there is not only vision but language as well. So we're going to look at that. So there are different tasks: object classification, detection, instance segmentation, and semantic segmentation. We have seen that these already. So language into computer vision tasks. So there is image captions. So captions, what does the image describes? Caption is there. Visual question answering. Suppose you're given an image and you ask the question, so someone answers. So these are the combination of vision and language that is possible. More are possible: text to image generation. You give the text, they have to generate the image. We have seen this is caption conditioning generation. Okay, text to video retrieval. Okay, natural language processing tasks, the search engine, spam filtering, machine translation, sentiment analysis. So from language models to LLMs. The GPT is there, GPT training. Okay. So these are also learning through self supervision only. But we're not going to go the details of this. Okay. So there are a lot of LLM models as you can see. Now we go to vision language models. Different tasks are mentioned here. The first important thing is clip. Okay, so in clip what you have, the training comprises of contrastive learning. What you do is you use a text encoder here. Okay, and there is the, so these are all untrained. Okay, so during the training time. Okay, there is an image encoder as well, so you can use a resonant or vision transformation, vision transformer. So vision transformer gives better performance. Okay, so these are put into embeddings of size n. Okay, both the cases. Okay, and then you match them contrastively. Okay, so what you do, if uh, so 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 the main thing you understand here, question number 6. Okay, let's see, or maybe let's see this one first, then we can see. So you can see that every means I1 is matched to every embedding in the text space. Okay, 1 to n. So whichever influence the first embedding of the image the most, that text will have higher score. So the higher attention score you can say, or softmax score you can say. So that is the thing. Okay, so the score is given by contrastive learning. If they are similar, if they're dependent, then it will place score placed closer. Okay, otherwise farther away. So this table is formed that way. Okay, and the model learns model learns how to compare these. Okay, and during the test time what you do, you give a sentence and it generates the image accordingly. Okay, so during the inference, let's go to question number 6 now. What was the, there is nothing much here. Reverse process is to remove noise. Okay, So there is now blip as well, bootstrapping language image pre-training. Okay, so let's see what we do here. Okay, so here, as you can see, so the image is passed to image encoder having a transformer, and the text is also passed to text encoder. Okay, ITC. What does ITC mean here? Uh, so there another text encoder is here. Uh, the text is passed through three encoders here. Okay, and a simple text encoder using self-attention image grounded text encoder. So what it means is that, so here what we are doing in the second text encoder, as you can see, we are using cross attention, comparing the image embeddings as the and the text embedding. So using cross attention between them. So, okay, there is self attention here and the cross attention comparing with the image. Okay, the third one, as you can see, image grounded text decoder. So it decodes back the text. Okay, so it generates the text. Okay, so that is the structure. One is the self attention one, cross attention one, and it's for generation. And the image has only encoder, so it seems like it is for image captioning task. Okay, or something like that, not generating image, right? This is it. Okay, we should do some questions now here. This one, the what is the effect of increase the guidance? These are also there. Okay, effect of guidance scale. Okay, less diverse. Okay, in the forward process of diffusion monitor, the data is incrementally corrupted by adding noise across t time step. If the variance of the noise added is beta t, which increases linearly with 0.3 at the first step to 0.2 at the last step over 150. So if it increases, it decreases linearly. So the decrease is 0.01 by 150. This is a decrease, right? Calculate total variance of the noise added over 150 times steps. Calculate average variance per step to calculate the total variance. So the model is there actually. Let us see that. Diffusion DDPM. DDPM. So it talks about adding noise, right? So what we are doing here is adding noise. Okay, so you have to do this. Okay, this is the equation. Let's see. What we're doing here is, so each time step beta t noise is added. Total variance added over 150 time steps. So that is what it is. So we have to calculate this one, right? 1 minus alpha t bar. Okay, so this is what we need to do, and bar is 1 minus product over s equals to 1 to t is 150 here. Okay, alpha s. Okay, now alpha s is defined as 1 minus beta t, beta s. Okay, so uh, this is one difficult task you have. How you do it? This is the variance, right? Am I wrong in this? The hint or something else, I think. Let's see. Average variance per step to calculate total variance. Sure. 150 steps will do this one, right? Average variance per step. So the average variance is here beta t. How have we done this one? It's not alpha beta, just average. Sure. Problem construction must be different then. Acha, acha. Okay, okay, okay. Okay, so this is a for different formulation. Okay, different than the paper. Okay, okay, yeah. So what you have to do is you just have to add the variances. Okay, divide by total. Okay, so that is 0.2 and 0.2 plus this. Okay, divided by 150. Considering a reverse process in diffusion model where the goal is to reconstruct the origin if the model correctly reduces the variance of the noise by 0.02 in each reverse step, okay, and starts with the noise of 1 at time step t equals to 50, how many steps are required to reduce the noise to 0.1? Acha. So the change is 0.9 and there are at time step 50. Okay, okay. Okay, so it starts with the noise of 1 at time step 50. Okay, so the noise is 1 at time step 50. How many steps are required to reduce the noise to 0.1? Acha. So that's the number of step is x. Okay, so each step 0.02 and reduce the noise variance to 0.1. So that is 0.9. Na? Hmm. So multiplying by 100, get 90, 45 steps. Okay. Yes. Classifier free guidance is technique used in diffusion models to improve sample quality without the explicit use of a classifier. This we have seen as well. If the following are false for self-supervised learning techniques. This is also we have seen a lot of repeated questions. And so this is what we are seeing already. I think I made the mistake that uh, so this is the assignment and this is the non-graded one. Non-graded one is different here. Okay, okay, okay. I wanted to put the non-graded one there actually. I made a mistake here. Okay, so we'll do the rest of the questions after some theoretical work here. So contrastive loss, really nothing much here. Zero shot learning. These are different experiments that was conducted. Okay, nothing much here. Encoder models are not straightforward to transfer to text generation tasks. So suppose given an image, we want to generate the text. Okay, so it is not that simple. Data's perspective, noisy web scraper text is suboptimal for vision learning. Okay, so that's the data problem. So now the blip model. Okay, so here blip model, what you have, the image encoder is there, and so this is it. Okay, but text encoder is there, encodes the text. Okay, and image grounded text encoder, which compares the image and the text. Okay, and this is the image grounded text decoder. Okay, so something like a GPT-3 decoder. So image grounded text encoder they fine tune. Okay, and lot of things here. So blip 2 is also there. The squaring transformer they use. Okay, lot of things here again. So another is the COCA model. Novel approach that amalgamates single encoder, dual encoder, and encoder decoder paradigm. This involves single text, image text foundation model encompasses the functionality of all three approaches. Okay, so what they do is there is image encoder and the unimodal text decoder is there. Okay, so they use cross attention between okay, so this unimodal text decoder feeds into the multimodal text decoder. Okay, so it takes also the image into account. Okay, and there is cross attention between the image encoder and text decoder. The losses are shown here. Okay, attention pooling, different things there. Fine tuning is also shown here. Okay, this was one of the things. Okay, let's see. Let's see some questions now. So, so let's still see this question, question number three, because it's very relevant to what we have covered till now. So, what does Byol do? So, Byol is no negative samples, one, three, right? And then we can pin it down with two, universal adversarial attack. Okay, so Moco is dynamic dictionary lookup 4-1, is the same. So, and there's gradient estimation, universal adversarial attack. Uh, so I'm not too sure. But I think the gradient estimation should be black box adversarial attack. Uh, can anybody say why or something otherwise? So it went wrong. Two should be four. White box. Acha acha. Oh, that is what I said, but I marked it wrong actually. Two should be four, right? And three should be two. Yeah. Okay. Consider the image colorization problem where we learn the colored version of a black and white image. Which will, that's the channel problem is there. So we will not go into the details of that. Color classification was there. Color learning problem. Somewhere here. Okay. So let's further move to the other lectures here. 5 is done, I think. Huh? 5 is not. 5 is done. Okay. 6. We move to 6 1. So these are the. There will not be much details, I think, here. So large language and vision assistant. Not much to learn here. So lava training is there. Okay. Video chat GPT. Okay, well, I think we should finish it off here. Okay. Any more doubts here? Any doubts? No doubts, right? So we finish. Any blogs about vision language model? Vision language models. Uh, I'm not too sure actually, but Facebook does most of the SSL in general. Okay. Well, there is one tutorial I referred to for SSL, cookbook of SSL. Okay, so I will share it on the notes section. Okay, so I do refer to this. Okay, it is a really good one. Okay, you can also refer to it. Summarized all the researches in the recent times. Okay, and VLM models also, I think any blogs you'll find from Facebook. I'm not too sure. I've seen few papers, but it is not my area, so I'm not too informed actually. Okay, so thank you very much. Hope you enjoyed the course. This is the last time we meet in this course. I hope the experience is well. You learned a lot of things.
So will there be IPNB file for coding and
No, there will not be.
all? Okay.
And best of luck for your exams. Mm,
Thank you, sir.
okay. So Ayer, Ahana, and Devosmita. It was really nice to teach you. I assume all the objective questions. I think there will be objective questions. There can be some calculation one as well. Put the number in. Okay, so Swati, we are finishing up now. Okay, uh, hope you learned a lot in this course. All the objective questions. Okay, there may be some numerical ones. And okay, it was really nice experience for me. Okay, okay. So thank you everyone. We will finish it here. Okay.
Hello, sir. Sorry, I just joined. Actually, I was thinking this call is at 6 o'clock. May I know if you have shared any links in the chat because I cannot see it right now.
No, I have not shared anything.
Okay, okay, no problem. Thank you, sir. Thank you so much for your session.
Thank you. Okay, thank you.